Okay, so this is actually the first time that we invited someone um, who is not a mathematician, who's going to introduce the speaker. And so today, Ruth Elizabeth is going to introduce our seminar speaker.
Thanks.
Welcome. Today's speaker is Professor Arun Ram from the University of Melbourne. My introduction includes both formal an formal part and an informal part. Professor Ram received his PhD from the University of California at San Diego in 1991. He was an NSF postdoc fellow at MIT and subsequently held other positions at the University of Wisconsin, Madison, and Princeton. Professor Ram moved back to Madison in 1999 as a tenured faculty member, associate, and full professor before moving to the University of Melbourne in 2007. I first met Arun 26 years ago at my first mass dinner at the University of Wisconsin-Madison, along with his girlfriend, fiance, and now wife, Jae Kyung Kim. As young math couples, we would get together in Chicago or Madison for math conferences, musical events, and culinary experiences. I should mention that Arun and Jae Kyung are very accomplished musicians and excellent cooks. One of my favorite memories of us when we would go to the India Mecca, Devon Street in Chicago, and meet with Arun and Jae Kyung for lunch together. When we were to arrive at the restaurant, the waiter would pass out menus, and we would just instruct the waiter to give the menus to Arun, who would then instruct the waiter on cooking possibilities, not in English, and after some discussion, would order for the table. Needless to say, Daniel and I have enjoyed some of our best meals when Arun has chosen the menu for us. So it is my great pleasure to have our longtime friend, Professor Arun Ram, here today at the UGA Algebra Seminar. I am looking forward to hearing him speak on integral modules for affine Lie algebras.
Thank you, Ari. Well, that's very, very special. I certainly didn't expect such an introduction from such a renowned and famous person in our family anyway. Ari goes, like you said, what is it? You said 26 years ago?
Yes.
I'm amazed. Yeah, time goes fast. I guess our girls are all grown up, all of us. And it's amazing. Very special times. I wish everybody could have been along. I guess John might have been at some of those with us, but it was a good time. Remember that old apartment. All right, thanks, Ari. I'll start with the mathematics, which is this paper with Finn and Yeping. As I was mentioning, Finn is a graduate student at San Diego now. He was an undergrad here, and Yeping is one of our representation theory core here in Melbourne. And we worked on this paper because I got really fascinated with these level 0 modules. This is for me the most amazing thing that I saw in in this game. And so I'm excited about it, want to tell everybody. So the story, I'll start with just loop groups to motivate loop groups. I wanted to make that, I don't know, it doesn't look like there are graduate students here, but I thought maybe there might be. And so I was gonna try to make the talk.
There are graduate students here, but they are in the actual seminar room.
Oh, okay, great. All right, so good. Then some of this will be hopefully appropriate. So loop groups, I'll call it LG0, but the way that I think about it is as follows. Of course, my favorite group in my whole life is GLN, right? And it's sort of the only group I really actually know. But GLN has a maximal compact subgroup. So there's a map here to maximal compacts. In fact, this is an equivalence. There's an equivalence of categories between reductive groups and maximal compacts. Going the other direction is complexification. And UN is really some symmetries of some space. Oh, maybe I should make it a bit smaller because I need to map into this. So this is UNC. And a loop in UNC is a loop, right? That's a loop. In other words, a loop is a map from the circle into the space of symmetries that we'll call G. So this circle is S1. And so a loop is a map from S1 into UN. But of course, S1 is really U1 of C. And so now we know what, if I complexify, that should be a map from C cross, because C cross is GO1. I mean, you can think of your loop, if I had something on the circle, e to the I theta, because that circle is in the complex plane. And so you can write e to the I theta as coordinates. And for each theta, you get a matrix, which is got a bunch of matrix entries, e to the I theta. So I could keep track of the matrix in the same way. If I had a coordinate here on C cross, then I get a matrix, Gij of that. And instead of thinking about this loop now, this Gij, this matrix G, which is a matrix full of functions and epsilon, that is an element of GLN with entries in polynomial, Laurent polynomials and epsilon inverse. So that's the motivation for the world of loop groups. And I wrote it over here that the general loop group, so I could do that for any reductive group, and LG0, if G0 is reductive, is for me G0 with entries in epsilon inverse. All right. But then you do this amazing thing. You add a central extension, and I won't write out the formulas, and what's called the loop rotation.
Right, Arun, can you sort of move your screen a little bit, because we're currently seeing, we're not seeing what you're writing.
Is it?
I
Percy is. It needs to go up, or what do you mean by move it?
Right. So I don't know. We are only seeing half of your screen.
Okay. You see the top half.
No, left half.
The left half. Oh,
yes.
Okay. So,
yeah, it's getting better. Can you still move it? There we go. Yeah, that's perfect. Yes.
Okay. Let me move this over here then. And how far to the right can you see?
It's too far to the left now.
Now it's too far to the left.
Yes.
Uh-oh. Okay. And now you can see the whole iPad screen?
A little more to the right.
A little more to the right.
Sometimes I have this happen at home, and if you click on view options at the very top on our computer, you can change the duration of the screen. Since other people aren't having a problem, I'm wondering.
Where exactly?
In the very middle top of the screen. Yeah,
Oh, I see.
you try clicking maybe switch your window.
Okay, I see. Yeah, I think it's solved.
It's solved.
Yes.
So maybe go back to what you were doing originally, Arun.
Okay, I'll go back to what I was doing, which would be preferred, yes. Okay. All right. So if I add this central extension and loop rotation, then I get a bigger group, which I would like to call G. That's the group I want, which has got a central extension to what I had before. And then I've got the loop rotation. The loop rotation is just the process of multiplying epsilon by a constant, but let's not worry about that. We get a slightly bigger group. And then a miracle happens. So the miracle is that this bigger group is a Kac-Moody group. Kac-Moody group. And what that means is that it's generated by SL2 subgroups, by SL2C subgroups. So in other words, I've got a bunch of maps, phi 0 from SL2C into G, all the way up to phi n from SL2C into G.
Can't take over my chair as well as your own.
And those n maps, the images of those n maps generate the whole affine Kac-Moody group. So I can really hang on to these SL2s, and that's what makes the theory work. Okay, so that's my setup is I'm working with this group, and it's going to be generated all by SL2s. Now there's a couple of reductions that we always make. So one of them is that we go to the Lie algebra. Algebra is isomorphic to my G, so that's my Lie algebra. And then I go to the enveloping algebra, which is an associative algebra. See, the Lie algebra is not great because it's not associative, but the enveloping algebra is associative. And the point is that if I want to look at G modules, I mean, we're doing representation theory. So I want to look at G modules. And G modules are the same as UG modules.
Arun, can you move the control for your QuickTime player up on your computer screen? The controls for QuickTime are in top of what you're writing on.
Yeah. Why is that not?
I think you can just drag it up to the very top and it'll be out of our way.
Yeah, I think it should have disappeared now. Is that right?
Yes, it did.
Okay, good. Okay, so of course, that's not what I'm really interested in. What I'm really interested in is G modules. And G modules are integrable Lie algebra modules, which are integrable UG modules. So that's the category that I want to focus on, category of integrable G modules, because those are the ones that are actually modules for the group G. All right.
What does integrable mean?
Integrable means the ones that come from the group G, the group so there are more, if I just look at the Lie algebra, there are more modules, and I don't want them all. I just want to study G modules. So those are the ones that either integrate up to G or are differentials of the ones coming from Roman G. Does that help?
A little.
Okay. Yeah, the Lie algebras have lots of modules, and we only want those ones that are rational representations of the group G. Okay, so since my group is generated by SL2s, subgroups, then UG is generated by SL2 Lie subalgebras. And I'm going to write down those generators. So there's going to be E0, F0, H0. That's a little SL2 subalgebra. En, Fn, Hn. That's a little SL2 subalgebra. And then I have these two extra components, this C cross on the left, which I'll write as which I'll write as K. And the C cross on the right, which I'll write as D. So this comes from C cross, and this comes from the other C cross. And all the rest is the SL2 bits. Okay, so that's how I'm going to work with it. Now, what do modules look like? So let's look at structure of modules. Well, the group has a big commutative subgroup. So T is large commutative. And it has a Lie algebra. G and H. So I think of G as the log of the Roman G and H as the log of the capital T. And that's because I've got this exponential isomorphism. So all the Lie algebras are logs of the others. Okay, so that large commutative subalgebra is how I'm going to pin everything. And then I've got symmetries preserving T. So that's the affine Weil group, if you wanted to build the affine Weil group. So W, it's all the automorphisms of the group G such that W of T is T. All right, so I don't like to distinguish between extended affine Weil group and non-extended and so on. I just look at all the automorphisms of the big group which preserve my torus. And those are the symmetries that I want to get my hands on. Okay, so now T has got is all commutative. So I can look at simultaneous eigenvectors for T. For T, which means that my module decomposes as a direct sum of eigenspaces for the action of T. So M lambda is the set of vectors in M such that if I take something in the torus, so if EH is in T, then e to the H acting on M is a constant times M. So eigenvectors for all elements of the torus. Or I could write purely in terms of the Lie algebra. It's all elements such that if I have something in the Lie algebra, then H acts on M as lambda of H M. So that's the eigenvalue. And now you can see what the eigenvalues have to be. So that's for lambda, which are maps from the Cartan into complex numbers. So taking H to lambda of H. And so another way to say it is that lambda is an element of the dual space of H. All right. So that's my setup. And we have, we can't forget our affine Weil group, because the affine Weil group is giving me symmetries W, which take M lambda to MW lambda. All right, so my whole module is built out of all these pieces, and then I have all these symmetries between them coming from the affine Weil group. So that's for W and W. And the integrability, so integrability gives me, so since M is integrable, then all of these lambdas, they actually have to live in an integral lattice. So these are all of the points lambda in H star, such that lambda of HI is an integer. Okay, so that's my setup. Maybe I'll remind you what the H's are. Let's get this for the, so my developing algebra is generated by these little SL2s, and the H's are those elements of the SL2s. And so I have some very, not the whole dual space, but just the integral parts. And now we're beginning to see why I get pictures like this of a bunch of integral dots on an integer lattice. So let me try to explain that picture, because this picture is for the example SL2. Example of when G0 is SL2. So in that case, the torus, it contains e to the ck, which is this central element k. And it contains the diagonal matrices, like e to the theta and e to the minus theta. That's a diagonal matrix in SL2. So the diagonal matrices will all commute. And it contains e to the gamma d, where d is this d from the extra C star. So theta, gamma, C are all complex numbers. Or if I were to look at the Lie algebra is, of course, the log of this group. So it's the span of K, H, I don't maybe call it H1, and D, where H1 is this matrix, right? So I can really write down this little three-dimensional Lie algebra, abelian, it's commutative, everything is commutative. And I want to look at eigenvectors for that. So I want to look at maps, the dual space, and the dual space I'll write as having three basis vectors, delta, omega 1, and lambda 0. All right, so for SL2, we actually get a three-dimensional space. And this was, for me, shocking, because usually I don't write the Weil group acting on a three-dimensional space for SL2. Usually we draw pictures of the Weil group acting sort of on a one-dimensional space, but it acts on H star generated by two matrices, S0, which is 1, 1, negative 1, 0, negative 1, 2, 0, 0, 1, and S1 is 1, 0, 0, 0, negative 1, 0, 0, 0, 1. So the affine Weil group, by its very nature, is acting on this three-dimensional space. And these are written in, these matrices are written with respect to that basis. And that's the action of the affine Weil group that we want to study. So you start to study this. You try to write down, what does the action look like? So W orbits on H star. So then it really divides into three cases. Already when you start to look at these orbits, you see three cases. First case is positive level. So positive level means that the coefficient of lambda 0 is positive. I mean, if you look at the action of these matrices, right, if I take a vector like A lambda 1 L in H star, if I think of that as a vector, a 3 in this basis as a column vector, well, then these matrices fix the L. So the action fixes the L. The coefficient L is positive. The L is fixed by S0. S0 and S1. So the level doesn't change when you act by the affine Weil group. It'll always stay at the same level. So now we find ourselves what the orbit looks like. So this is a picture of the orbit here. And I've just drawn, I started with one point here. Let's say I started with this point. And then I acted by I want to act by these two matrices, S0 and S1. So if I act by S1, then I'll end up here. And then if I act by S0, I'll end up here. And then if I act by S1 again, I end up over here. And if I act by S0, I get these. So this billiard path is actually the action of the affine Weil group on, in this case, it's level 2. So the L is 2 for this little example that we're drawing here. So this is L equal 2. And then you find this miracle happens again, that after you look at this action, all of the points are sitting on this parabola. So at level 2, you got a parabola like that, and you've got this billiard ball moving within the parabola, and that's the action of the affine Weil group. There's nothing I can do about it. I just calculate it. All right. And then, but if you go to a slightly different level, then you get a slightly different picture. So you can see what happens here is that the parabola gets tighter. The old parabola is this one, And the new parabola is the skinnier one. And that's as the level goes down, the parabolas get more and more skinny. And then you can do negative level. So if I do negative level, let's see, then the parabola changes direction and becomes this way. All right, so you positive level and negative, I did the same thing. I calculated the orbit. And if you do level 0, then another amazing thing happens. So let's find the picture for level 0. So this is the picture for level 0. So now that parabola is just these two straight lines. And you see the billiard going back and forth between these two straight lines. So depending on what level you start at, the action of the affine vowel group preserves the level, but it changes shape. And these points here that I've written are the orbit representatives. Well, first let me show you the beautiful picture of, because I'm very proud of it, of the, so these are all the levels. You can see that the positive levels are up here and the negative levels are down, and the two parabolas are going in opposite directions. And then if you look at level 0, you see those straight lines. So you've got parabola this way for positive level, parabola this way for negative level. And in the middle, there's this singular feature. You can see exactly at level 0, something happens and the parabolas become straight lines. So that's the picture of the orbits. And this picture here are the representatives of the orbits. So for the positive level ones, I'll choose a representative, say this representative of the whole orbit. And for the negative level ones, I'll choose, say, this representative, because I don't want all the other ones on the billiard. And for this one, I'll choose this representative. And when you graph those representatives, you get these three sections. So representatives of the orbits. I call it E hat, which has the positive part, the 0 part, and the negative part. And the 0 part is all of those points, A delta plus lambda 1 omega 1 plus 0 lambda 0, where lambda 1 is a positive integer, non-negative integer, and A is a complex number. That's the 0 part. And the positive part is all of those points, A delta plus lambda 1 omega 1 plus L lambda 0, such that L now is a positive integer. So maybe I should have color coded these. So these are the red points in the picture over here on the left. These red points are the positive ones. And the level 0 ones are the green ones, which are down here on this line. And so going red here. So here I can have L being a positive, the level is positive, and the lambda 1 is running in between 0, 1 up to L. All right, so that's this cone that we're seeing, this top part of this cone. And those are the representatives. Okay, so that's the first step in understanding integrable modules, is to get your hands on the Weil group orbits. Because for each element of the Weil group orbit, we're going to build a module. So extremal weight modules. Which are called L lambda. So I let lambda be an orbit representative. So I start with one of these points in this picture. And then I'm going to build a module. So build L lambda, an integrable module. And the construction doesn't depend on the level. The construction works just generally for all levels at the same time. So step one is start with one vector. Which I'll call V lambda. So that's an eigenvector for the action of the carton. So if I was thinking category O, then that's a highest weight vector, and I start with a highest weight vector. But I'm not in category O anymore, so necessarily. So I just have to start with one vector somewhere. Maybe we can pull up a level 0 picture so that, yeah. So we'll start with one vector here, let's say at this place. Oops, it didn't. We'll start with this vector here. Okay. And then you move it around. So this is step 2, around with W. All right, so now I get a whole bunch of vectors, V sub W lambda for W and W. So W acting on V lambda is VW lambda. You remember that W was a map from the lambda weight space to the MW lambda weight space. So I'm just taking that vector V lambda and moving it all around. And that becomes all of these bullets that are around the edge here. I get all these bullets. Okay, so I have a whole bunch of points around the edge of my module. And now I have to spread it. So step 3 is spread it with UG. So you remember that UG is generated by E0, EF0, EN, FN. I already have the K and the D. The K and the D are already taken care of here. So I have to spread it with the E's and the F's. And then you have to put relations. Put relations. And these are the relations. So I want 0 to be Fi of W of V of SIW lambda, which is Fi of W lambda evaluated at HI plus 1 VW lambda. Let me write the other relation and then I'll explain. And I want EI of W lambda HI plus 1 acting on V SI W lambda to be EI V W lambda to be 0. So how do you interpret these relations? Well, you think of VW lambda over here and V SIW lambda over here. For SL2, I just have S0 and S1, but for GLN, I might have lots more. And then you act by FIs. And the FI spreads this in some integral steps. 1 FI, 2 FIs, some number of FIs. And then if you do that number of FIs too many times, you get 0. So that's what this relation is saying. If you start with VW lambda, you apply this FI just enough times to get to the other side of the billiard path. And then if you apply it one more time, you get 0. And the same with the E's. If I apply EI a whole bunch of times, EI, and then I apply it one more time, I get 0. So that's what these relations are. And this is this beautiful construction. So this constructs an integrable module. L lambda is an integrable module. This construction is, Kashiwara wrote it down. And if lambda is positive level, so if lambda that you started out, then this is simple, is irreducible. And if lambda is negative level, and let me point out that if you start with positive level and it's highest weight. But of course, from our pictures of the orbits, if we look at an orbit here, it's clear that it's highest weight because the parabola has got just one thing, it runs out of room up at the top, right? And if you start with something that's negative level, then L lambda is simple and lowest weight. Because if I get a parabola going this way, then down at the bottom, you run out of space. But if lambda is level 0, then it's neither highest nor lowest weight. So it's not in category O and it's not in dual category O either. It's a new place. But you might know that that if you go ahead.
Is it still simple?
Most of the time, but not always. I can't just make a statement that it's simple. No, there's, yeah, it's more complicated. Let's just say it that way. But if you take two modules, so if I take L, say, so let's say I took A1 plus lambda 1 omega 1 plus L1 omega 1, and I tensor it with A2 plus lambda 2 omega 2 plus L2 omega 2, well, I get a bunch of stuff, but all of this is level L1 plus L2. So if you tensor two modules, the levels add. That's my point. But that means that level 0 modules form a tensor category. They're closed under tensor product. Whereas none of the other levels are closed under tensor product. And I think that that's an amazing category, although it's still not very well understood. I would like to claim that that's the source of conformal field theory, but I don't know. That's of CFT. is that. Anyway, okay. So how long when do I need to stop, Adik?
I think 7:55.
7:55, okay, great. So we've built these amazing modules, and they have characters and they have crystals. So the character formulas for positive level and negative level, actually, let's see if we've got some crystals here. Yeah, so here's an example of a crystal where you can see how the Fs have spread the Weil group orbit and gotten all of this extra stuff in the middle. But because they've got crystals, that's really the reason why you can write character formulas. And for positive level and negative level, we have these Weil-Katz character formulas. But at level 0, it's quite amazing. There are character formulas that I had never seen before. So the character of L lambda, if I'm at level 0, so let's let lambda be in E hat. And then let's take this Kashiwara module, L lambda, at level 0, which pictorially, now this looks like, it looks kind of like this. All right, so it's sitting in a tube and it's got all kinds of stuff inside the tube. So its character is equal to the character of something that I'll call RG lambda times EW naught lambda, and I put a tilde there for, okay. So it's a product of two factors. This factor is a non-symmetric Macdonald polynomial. And here the Q is keeping track of the delta. So as you move up and down this, you can keep track. And you can see in this picture already that this is periodic. If I take some section of it, that didn't, I don't know if that works so well. If I take some section of it here, then it repeats. And that's this product that we're looking at. That's this product. And this non-symmetric Macdonald polynomial is some little finite section. So let me write that. This is a finite section of L lambda. And this other factor here is the periodicity. This is the big infinite part. Infinite. And let me write the formula for the character of RG lambda. The character of RG lambda is 0 q to the m1 times the product k going from 1 to m1 minus 1 of 1 on q1 minus q to the k up to 0 q to the mn product k equal 1 to mn minus 1, 1 on 1 minus q to the k. So this is if lambda is m1 omega 1 plus mn omega n. So you down here at level 0, we're looking at these green points, and the green points are always multiples of the fundamental weights. And then I take this crazy function where 0q is Q inverse over 1 minus Q inverse plus 1 over 1 minus Q, which is Q to the minus 3 plus Q to the minus 2 plus Q inverse plus 1 plus Q squared. So this is really an infinite periodic thing. It's just pushing it on a big, or I should do it up and down. It's a big tube. And I've got some little finite piece and some infinite periodicity. And you can really write it down, combinatorial. And the McDonald polynomials appear. I think it just, for me, this formula is just completely amazing that it's possible to combinatorially control a module like that.
A question, is that your formula?
No. Sorry. That's, thank you for telling me. That's, oh boy, it's a combination of a whole bunch of people getting put together. So Nakajima, Bogdan, Ion, Fourier-Littelmann, and maybe Braverman and Finkelberg. And of course, Kashiwara. Kashiwara did the first examples, and then it took a while to get processed, but now we understand that pretty well. There were important steps from Nakajima and Ion and Fourier-Littelmann in particular. Yeah. And then I think Braverman Finkelberg put it all together in the end, all the different steps. Okay, I have just a little bit of time left, and I want to mention the geometry. So G has upper triangular subgroups. And because it's now, it does not have just a single conjugacy class of Borel subgroups. It has some really distinct ones. So the first one is I plus, which is all of those matrices. Let me just write it down for SLN plus 1, such that if I plug in 0, so first of all, there are matrices that can specialize at 0, epsilon at 0, and I want those to be upper triangular once I specialize them. And then it's an old theorem of Kumar and Mathieu. So G mod I plus is the affine flag variety. And if I take lambda defines a line bundle, on this affine flag variety, G mod I plus, and if I take global sections of that line bundle, then that's isomorphic to L lambda. So that's Borel-Weil-Bott, but now in the affine case, which is Kumar and Olivier Mathieu. And now that's for positive level. This is positive level. That this theorem holds for. And if you go to negative level, negative level, there's a similar thing. You have an I minus and a G mod I minus and a similar theorem, which is essentially the same, like positive level. But now, if you go to level 0, there's a new group, I0, which is all of those matrices in SLn+1, where now I take both, I allow my Laurent entries, I take epsilon and epsilon inverse, but I force the matrix to be lower triangular. And G mod I0 is called the semi-infinite flag variety. And if you do the same game, so you take lambda, which is now in level 0, defines a line bundle. And you take global sections of that line bundle, but now on the semi-infinite flag variety. Then this gives you that extremal weight module, the Kashiwara's module. So this is Braverman and Finkelberg, who explained this geometry. So you have a Borel-Weil-Bott theorem for positive level, for negative level, for level 0 as well, which means that you can do all your favorite geometry. Okay, my time is up. I'll stop there. Yeah.
Okay, thank you very much. Any questions? So we have a question here. I'm just going to listen to it.
Yeah, is the character formula at all related to, say, equivariant K theory in the way that the ordinary violent character formula is related to equivariant K theory?
Yeah, so are your character formulas related to K theory or equivariant K theory in a similar way to, I don't know, the ordinary case? So Bill
yes, the answer is absolutely yes. And Kato, Naito, Sagaki have given a Pierre-Chavalet formula even. So not only do you have Schubert classes and everything, you can take your line bundle L lambda, and multiply it times the structure sheaf of your Schubert variety. And expand that and expand. So yes, we have wonderful K theory and wonderful K theory ring that works just like the ordinary case, except that you have to use the geometry of that level 0 orbit. So you have to use a level 0 Bruja order. But the answer is yes. And they have written it down rather nicely.
Thank you.
Okay, thank you. Any more questions?
So where do the non-symmetric McDonald polynomials fit in terms of the K theories? Is some explanation or some interpretation of that?
Okay, so Bill asks about the non-symmetric McDonald polynomials. Do they have an interpretation in terms of the equivariant K theory?
Yes. So there are two parts to that question. So one part is you see, it's a bit funny because we've got the character of RG lambda, and then we've got this non-symmetric Macdonald polynomial. So I have to pick out this finite part. And this is this infinite part. So this infinite part is actually the shadow of a Heisenberg subalgebra. Subalgebra of UGs. It's the homogeneous Heisenberg. And that Heisenberg is playing the same role inside the Daha, or maybe I should say it better. If I squash that Heisenberg, so if I take the spherical subalgebra inside that Heisenberg, that's the spherical part of Daha. And so the rest of the Daha part that's left is causing these Macdonald polynomials. But it is important that it's only at t equals 0. So t equals 0. So it's a little bit of a degenerate version. So you only see de Mazur operators. Yeah, de Mazur operators. It's not the actual full Hecke action of the Daha that appears. But I think there's definitely much more work to do on this learning how to separate the Heisenberg and the finite part. We don't have that under as good combinatorial control as I would like.
Thank you. Okay, thank you. More questions. Okay, I don't think we have more questions here. So can you maybe quickly remind me about the I minus? How do you define this?
The I minus, it's exactly the opposite of the I plus.
Okay.
So I minus is all of those matrices, which are now polynomials in epsilon inverse. And we want to put it so that when we evaluate them at infinity, then this is lower triangular.
Okay, yes.
So, but that's a good choice for I minus.
Mm-hmm. Okay. Any more questions? The people at home? Okay, doesn't seem to be the case. So yeah, let's thank Arun again.
Thanks a lot, Arun. That was really good.
Thank you.
I'll see you again.
Thanks, Arun.
Thank you.
Stay healthy.
Yeah, thank you.
Thank you. You too.
I enjoyed your talk.
Thank you. Thank you.
It's very interesting. So thank you.
Yeah, Bill says it was very interesting.
Great, great, thanks. So Ari, let me call the girls, okay?
Okay.
Can you stay on for a bit?
Yeah, I'll stay on, don't worry.
Okay, okay.
The best of the 2/3 of the Ram family.